A distinct privilege, obviously, to welcome our speaker, Dr. Gavin Schmidt, all the way from New York. So let's give him a round of applause to make him feel excellent. I wanted to begin with a short story of a man who was walking home very drunk.
Not me.
And complaining loudly to God about his own problems. He found a preacher by the river baptizing people by submerging them in the water. The preacher asked the man whether he wanted to be baptized so that he could see the Savior who would take away all his problems. The man did not hesitate a second and agreed to be immersed in the river to be baptized. The first time, the preacher immersed the man in the river for a few seconds. Then he pulled him back up and asked him whether he had seen the Savior. And the man said no. Then he said, let's try a second time. The preacher immersed the man for a second time, but this time a little longer. And then pulled him back up. He asked him the same question. Did you see the Savior? He said, no, I didn't see the Savior. The preacher then, of course, was frustrated. Then he decided to take him back again to the river. And then, but this time, a little longer, until his legs started kicking about, and then he pulled him back up again, and then asked him the same question. For heaven's sake, have you seen the Savior? And the man wiped his eyes, coughed a little bit, and caught up his breath, and asked the preacher, are you sure the Savior fell in this place? Now, clearly, there are communications breakdown between the man and the preacher. even though both understand that a change is needed. When it comes to matters of climate change, nothing is simple. From the heroic construction of a model with complicated technical components that attempts to reproduce the climate system, to communicating and explaining climate models to a general audience through the media. Our speaker, Dr. Gavin Schmidt, is a master of both worlds. As a leader of NASA Goddard Institute for Space Studies, he is forced to balance his media persona with his role of an institutional leader and also a spokesperson. Not an easy task. Today, he is going to talk about his own journey. How did he get there? Or what step did he take to get there? How did he get involved in what he's doing today? What excites him about it? Ladies and gentlemen, help me welcome Gavin Schmidt!
Thank you very much. My first instinct upon being asked to do a Maniac talk was one of horror. I'm still young, I said. I have potential. And Charles said, yeah, no, you had potential. So now it's time to talk about what you did. Okay, so this is where I'm from. Somebody asked me this just now. This is where I'm from. A totally nondescript, uninteresting, small, tiny part of the UK. And you can see, like, where all the names of interesting places are. It's nowhere near any of them. It is so uninteresting that in the entire history of my high school, precisely 2 people have done anything of note. Me, who left and went to NASA, which they're very impressed by, and Zoe Sugg, who I don't know if you might know. She goes by the name of Zoella, she does something on the internet. I am obviously a tremendous success. I have 31.8 thousand followers on Twitter. Yes, impressive. No, yes, impressive. Thank you. 13.5 million followers on Twitter, and has a book, her own brand. Anyway, so in terms of, it's interesting that they chose to put me first, but really in today's world, Zoe has been far more successful. So I'm not even the most interesting person that's come out of my own high school. So what was I doing when I was in high school? This. All I really cared about was mathematics and doing problems and trudging through problem sets and learning more about it and getting very excited by Martin Gardner and Scientific American and all the rest of it. And so this was really my only thought for the future. I shall do maths. And when I was 16, that was kind of easy. I will go and study maths at maths, not plural, because there's more than one. I will do that, and I will study that at university. And I was quite good at what I was doing, and so I went to university, and I went to a very pretty university. This is Jesus College, Oxford, and it's very pretty, and it's very nice for people who like that kind of thing. But most of the time that you're there, you know, you're too kind of caught up in everything to ever really pay attention to it. So now I enjoy going back, but at the time I really didn't appreciate it very much at all. And I spent most of my time perfecting my pool game, which actually is still not very perfect. But I spent more time playing pool than I did on mathematics until about the last 6 months of the whole course. And the UK is very interesting because instead of like amassing credits and GPA points as you go through everything, it's an all or nothing, one massive exam right at the end where you have to disgorge every single thing you've learned over the last 3 years. And that means that you can totally coast for 2.5 years of your degree and only actually apply yourself in the last 6 months and do extremely well. So that was something I learned, but don't do that at home, kids. But at the end of that, I was still following that path. I was saying, oh, mathematics, that's what I should do. But you get to the end of your undergraduate degree and you're going, where does this go now? It doesn't go anywhere. And so I decided that I would take some time off. I took some time off and I came to the US for the second time and I was in Boston, and I just decided to just do some random stuff. So, okay, hold on. Okay, so I'm going to intersperse this talk with typical conversations I have had through my career. Okay, so again, typical conversation at a party at around 1985, right? So when I was still an undergraduate. So a random person asked me, "So what do you do?" "Oh, I'm a mathematician." I was terrible at maths. And I said, "Well, no, it's really not so bad." "Okay, bye." That happened a lot. So when, at the end, I decided to work for a high-class establishment. I got a job as a security guard at the Gucci store in Copley Plaza in Boston. Quite frankly, the most horrible people I have ever had the pleasure of working with. Like, horrible human beings. The shoppers were fine, but the staff were just the worst. Interestingly enough, I also had a gig at Woolworths in Downtown Crossing, which has obviously since closed. Actually, I think the Gucci store is closed as well, so this dates me. The Woolworths people were actually very nice. We spent most of our time picking up people's shoes that they'd left when they were stealing a pair of shoes from the really cheap shoe aisle. And you really didn't begrudge them stealing a $10 pair of shoes. So. And then I worked for Avis Car Rental for a little bit. This was out of Logan Airport. Some of you may have flown through there. And you may not know, but the Avis lot and the Hertz car lot are on opposite sides of the street. And one Sunday morning, when I really wasn't paying too much attention, I took my Avis car and I drove it into the Hertz lot through the fence. And instead of promoting me, because I took out 3 of their cars for only 1 of ours, they fired me. It was outstanding. So anyway, so I moved on from there. I worked in Australia. I worked as a waiter in a very nice cafe in a not very nice part of town, but it was nice and friendly. I picked grapes in the Swan Valley, and my best job ever, and including the job I have now, the best job that I ever had was running a youth hostel in Perth, Western Australia. Let me recommend it to all 21-year-olds. It was great. So I got bored with with just like doing nothing, and just really the only intellectual contribution I was making was the crossword every week, and they would, you'd buy it. It's a cryptic crossword, the UK crosswords, not your everyday crosswords. And I would do that every week, but it was kind of tedious. And I was thinking, I should do something more. I should do something more. So I went back to London, and I was thinking, well, maybe I should do a PhD or something. And I thought, well, how does one do a PhD? So I just went to a maths department at the University College London, which is in central London, and I went to the office and I said, I'd like to do a PhD. And they said, you can't just come in here and tell us you want to do a PhD. There are deadlines, there are forms, there's a whole process that you should have been following. And I said, I'm terribly sorry, I really didn't mean to mess with your system. I didn't realize. And they said, well, okay, but go and talk to that guy over there. And I went to talk to that guy over there. And he says, I just got this thing funded. When can you start? And I said, I was going to go on holiday again, and I'll be back in about 2 weeks. He said, fine, just come by. And that was it. And it turns out that the PhD, what it was going to be, it was in a maths department, so I felt pretty secure that it would be of some interest. And it turns out to be on the calculation and stability of topographic Rossby waves. So these are waves that exist in stratified flow because of both the stratification, the rotation of the Earth, and the topography. And so there's an interesting interplay between changes in topography and these wave modes and things like that. And it turns out that the people who'd been calculating these things had not been doing a very good job, and it was actually quite an easy thing to come up with a much better way of doing it, involving Green's functions and the divergence theorem and all the rest of it. And so I did that, and it just seemed very straightforward. And there was an interesting side effect. So, typical party conversation in 1992. So, what do? I study waves in the ocean. Does that involve dolphins? No, but it's... okay, done. But progress had been made. When I finished that, I had a big change. It turned out that actually nobody really cares very much about topographic Rossby waves. And so the 4 people who did care about my PhD did not have any money, and so I had to throw the net a little bit wider if I was going to get a job. And so I threw the net wider. I talked to Lawrence Misak at McGill University, and he says, I used to do stuff like that when I was young, but we're doing climate now. Climate is the thing. And I'm going, well, that sounds good. And he says, what we're going to do is we're going to do models of the thermohaline circulation and understand its role in natural variability in the past. And I said, that sounds fascinating, absolutely fascinating. And I remember putting down the phone and turning to my supervisor and saying, what is the thermohaline circulation? Is that important? Anyway, so I arrived in Montreal, and actually it looked a little bit like that. I arrived, it was, I think, December 29th. There was a massive snowstorm. I was totally unprepared to the extent I did not even have a proper winter coat and no long underwear or even any boots. And the first thing we did, of course, was go shopping. And so this was a whole change of climate and a change to climate. And the interesting thing about McGill at that time was that it was all new for them as well. And so they didn't really have any big plans about what they were going to do. And so they just kept inviting, they had all this money, they kept inviting interesting people from all over to talk about, tell us about climate from this perspective or that perspective, and from a huge range of different people. And so for somebody who also did not know anything about climate, this was a fantastic opportunity. I was just like soaking it in. Like, tell me more. And I was very kind of open-minded about what it was that one might do as a researcher. But of course, I'm a postdoc, so you're all going through that kind of mild case of imposter syndrome where you're going, can I really make it as a researcher? Are my ideas at all valuable? Can I stand on my own, or am I always going to be like kind of traipsing after somebody else who has better ideas than me? And so I'm actively looking for, what can I do that's going to make a difference? What can I do? What can I do? What can I do? And so what I ended up doing was playing around with a relatively simple there's only average model. So like 3 dimensions is too many dimensions, so you reduce it by 1. And so while you're able to churn out a lot of results, you're always kind of suffering from dimension envy. Right? All of your friends have got 3 dimensions, and you've only got 2. But I wrote a couple of interesting papers and did some interesting mathematics. And this is, for instance, if you go back to really warm climates in the Cretaceous, you can have situations where you have warm water that's so dense in the tropics that's where the overturning stream function comes from, or if it's salty in the poles, then you get it from over there. And that makes a big difference to how much heat you're moving through the ocean. So, there was kind of interesting things there. And of course, this was related to the Cretaceous, right? Okay, so remember that. Because my first media interview ever, so this is in 1995, I'm in McGill, it's in Montreal, and I'm asked by a French TV journalist about this. And he says, comment était le Crétacé? Right? So what was it like during the Cretaceous? Right? So it was in French and with a heavy Montreal accent. I could do that for you, but if anybody's watching, that would just be too embarrassing. And I said, chaud. It was hot. And he said, à quel point il faisait chaud? So, like, how hot? I said, très chaud. He said, thank you very much. And I thought, oh, this media thing isn't too bad. I could get used to this. This is a true story. At the end of my time at McGill, I was, again, losing the thread a little bit. Like, where am I going? What am I doing? Do my ideas have any value? I was very lucky to get to apply for and to be awarded one of the NOAA Climate and Global Change postdocs, which is a great program, which is somewhat under threat at the moment, but it has an absolutely stellar cast of people that have gone through that program. And I'd written a proposal to work with somebody at MIT. But for some odd reason, the powers that be on this program said, you know what, we've given too much money to MIT. We have to be a little bit fair. We have to distribute the money more widely. So you can't go to MIT. And I said, but this proposal that I wrote can only be done there. And they said, yeah, I mean, can you just do something similar, vaguely similar? And I'm going, well, I guess. And I said, but where? And they said, well, just find somewhere. And so basically, I had money, I had a vague topic, and the ability to go anywhere in the country. So what does one choose? And what does one base those choices on? Oh, well, you're all looking at me blankly. No, it's like, where was my girlfriend living at the time? So my girlfriend at the time was living in New York because she hadn't been able to get a visa to come to visit me in Montreal. So we were doing this kind of New York-Montreal thing. And I said, well, you know what, can I go to New York? And they said, sure, just find a host. And so I came to New York. And here I am, what I think of as a bright, bushy-tailed postdoc with his own money. And I go to all the places around New York where I could possibly, I think, find a home. So I went to Lamont Doherty, and everybody there, really, they just really wanted me to work on very, very, very specific and kind of little things. I'm going, don't really know if I want to do that. I went to Princeton and GFDL, and nobody had the time of day for me. Like, everybody was too busy. And I thought, free money, and you're too bad. So I didn't really feel very welcome there. And then I went to GIS, and I called up one of the people there, David Rind, who some of you might know. And I said, I read one of your papers once about Cretaceous climate and ocean heat transport, and I've done a little bit of work on that. I'm in town. Would you like to? And he said, oh, come on by. And we sat in his office, and he brought people in, and we sat there for about 4 hours, and we talked about everything, from the modern climate to the future climate to the past, modeling, data, comparisons, the history of everything. And I was like, oh, this is fantastic. And then we went out for a beer afterwards with a bunch of people. We went to, like, a dive bar, which is no longer there, thankfully. And then we carried on talking, and I go home. I go back to the apartment after that, a little woozy, and like just going, oh, this is my place. This is where I want to be. And so the next day I said, is it okay if I go to GIS? And they said, sure, that's fine. And so I ended up at GIS. A little bit randomly, I admit. So this is GIS for those of you who don't know it. This is Tom's Restaurant, which was a famous exterior scene for Seinfeld. Also Tom's Diner, if any of you remember Suzanne Vega, this was Tom's Diner. And it's just a couple of blocks down from Columbia University. And in fact, you still have to fight your way through crowds of tourists photographing the building every day in the morning. Oh my God, it's the Tom's Diner. And it's like, okay, get out of my way, get out of my way. We're renovating at the moment. So right now, the 6th floor is a building site, and the 7th floor looks like the Superdome after Hurricane Katrina. And in about a year and a half's time, or maybe a decade, we will have a beautiful new conference center in here that you will all be most welcome to come visit. So that was 1996, I started there. So that's 22 years now I've been at GIS, which seems like a long time. And the one idea that I had that stuck was related to these things, water isotopes. And it turns out that water isotopes are a bit of a gateway drug to that whole like knotty issue of modeling. And the reason why is this. So why does anybody care about water isotopes? Water isotopes are what you're measuring in the ice cores when you're interpreting a temperature, right? So your temperature changes over the last 110,000 years from the ice cores, they're water isotopes. The temperature changes that we're inferring for the whole of the Quaternary or going back to the Cenozoic or even further back, those are all water isotope measurements made on small shells of small creatures that live in the ocean, and their shells fall into the mud, and then you analyze the shells in the mud. And these shells are made of carbonate. The O in the carbonate gets its isotopic signature from the water in which the shell was formed, plus a temperature signal. And so conflating the temperature change and the water mass isotope change has been one of the fundamental problems in paleoclimatology since the 1960s. But if you want to understand how water isotopes change and how they get recorded in these carbonate shells and also in cave records, in lake records, in corals, you have to understand a lot about the system. You have to understand how things change during convection. You have to understand how things change during evaporation and rainfall. There's interesting things that are going on at the tropospheric, stratospheric boundary. And of course, there's a whole bunch of things that are going on in the ocean that is both mixing and diffusing these signals away. The impact of sea ice, it turns out that that's important to include as well. And my big insight, such as it is, from all of that time at McGill, was that people had not done this problem properly. People had, for a long time, worked on atmospheric models of the isotope changes to some good effect. But nobody had really done the ocean part, and nobody had done the coupled part. And it seemed to me, if you're going to connect an isotopic signal that you're measuring in a foram at the bottom of the ocean, and you're going to compare it to an isotopic signal that you're measuring in a cave in China or an ice core in Greenland, you really need to understand how these things are coupled. And I thought, I shall model this. I shall do this myself. Yes, on my own. And so I came to GIS, and I said, this would be a worthy project of my time. And everybody was very polite, and they said, oh, that'd be great. While you're doing that, you might want to do a few other things. And I said, oh, well, okay, I can probably squeeze those in as well. So we did some interesting things, like so you know, my first Nature paper was about changes in Northern Hemisphere winter climates, and it made a prediction about how the North Atlantic Oscillation had been increasing up until that point, and how it would continue to increase because it was being driven by greenhouse gases. Obviously, the day that this was published, that trend that you saw in the data completely reversed and disappeared. And so we had then 10 years of people saying, no, there's no effect on the North Atlantic Oscillation by greenhouse gases, at which point I was oh, okay, well, we made a mistake. Okay, who knows? Until now, of course, the trend has come back, and so now, oh yeah, we're totally vindicated. So that was fun, and the reason that this came about was because Ron Miller, who's now my deputy, and I were both printing out some analyses on the same printer. And his analyses were kind of interleaved with my printouts. And it turns out we were calculating the exact same diagnostic, the change in the sea level pressure over time. And I'm going, oh, well, that looks like my diagnostic. And he says, oh, well, that looks like my diagnostic. What's going on? And we got together. We worked out that we were looking at two different sets of model runs that had very different behavior, which was the genesis of this paper. So that was fun. But it turned out, I mean, other people knew, but it was news to me. It turned out that adding whole new coupled systems to like early kind of first or second generation coupled models was actually quite difficult. The tracer code that worked for the isotopes was in this version of the model. The up-to-date convection schemes, which had better accounting for all the different things that happen to water, was in this version of the model. The coupled model was a totally different branch of the model entirely, and actually was very little to do with any of the others. And then the tracer code was in yet a third variation on the model. And it turns out that our version control system, I can say this now, I probably couldn't have said it then, but our version control system, circa 1997, had totally fallen apart. Like we had our own kind of homemade way of doing it that was brilliant, but it had got out of control. And so nobody really knew what versions anybody else was using. Everybody else was doing their own development, and it was a total mess. So in order to do my one big idea, it turns out that I had to bring the coupled model in, I had to bring the convection in, I had to bring the tracer code in, I had to bring everything had to go in together. And it turns out that was a job, and it ended up being a job that involved almost everybody at the Institute. And you can see how many authors there are. I think there's 45 authors on that paper. And you can also see when that was published, 2006, right? So in coming in 1996, it took me 10 years to build a model that allowed me to do the thing that I wanted to do in the first place, which was then published in 2007. But all of that work, everything we needed to do for that had to be done for everybody. And so that put me in a position where I knew a little bit about every single part of the model, and then suddenly became like the new Gary Russell. Gary Russell had been the person that knew everything about the model. He'd kind of given up on that, and now it was me. And the reward for that is being the first author on these papers, which get quite well cited, if not very well read. Okay. Yes, so that was in 2007. So, I'm feeling a little happier about myself. I'm doing all these things. I know a lot more about the climate system than I did. Okay, now I'm going to venture forth. No more patsy interviews with Radio Canada. I'm going to go into the tiger's den. So Alexander Cockburn was a columnist, English guy, very left-wing, but a total climate change denier. And he was writing in New York press around this time. And some of you will remember the Harries et al. Paper in 2001 in Nature, which compared some of the old image spectral results with some of the newer stuff and showed very clearly that if you looked at the greenhouse gas absorption lines over a 30-year period, 25-year period, you could see where the changes in that concentration of the greenhouse gases had led to changes in the absorption specific spectra, right? So it was a very, very good paper. And what it showed actually was that radiative transfer models were very, very good, and that our understanding of that whole thing was excellent. But this guy got some very, very bad advice and totally misread the paper. He even printed a picture from the paper in this kind of popular column. And he goes on and on at length about how this is a terrible thing. Anyway, so one of the things he says is the models have been disastrously contradicted because he doesn't understand anything. Yes, it does, and it's not unusual. And like I've subsequently gone back, you can see the same things for many, many decades before that as well. And so I wrote a letter to the editor, which included, among many other things, your writer is seriously confused. You've misunderstood this, and this, and what you're actually concluding is completely the opposite of what you should be concluding. Now, I'm not quite sure what I was expecting. Gratitude? Well, I didn't get that. Schmidt's invective beats his science. He cannot focus on the details. I hope Schmidt isn't advising anyone on anything scientific. Oh, dear. At which point I realized that this whole communication thing was a little bit more tricky than I had thought. So, well, I still went to parties, right? 2004. I'd actually broken up with the girl I'd moved to New York to be with, but I was still in New York, and actually so is she, and we're still good friends. But anyway, so typical party conversation in 2004. So what do you do? I study climate change, right? I've grown into this. Oh, like that movie? Well, actually, that wasn't. Yeah, okay. Some of you might remember that movie.
All our grid models are worthless.
I don't think grid models are going to be a lot of help here.
Nope, they're not. Some of you might also remember that the producers of this movie did not sign a Space Act agreement with NASA. And there was a memo that went out from Public Affairs instructing us all not to discuss either the science fiction or the science fact associated with this movie in any venue whatsoever. That was a little draconian, even for the Times, and I think that found its way to the front page of the New York Times in very, very short order. Not through me, I hasten to add, but possibly somebody I was next to. But anyway. And so this movie is very, very interesting and actually has a bigger role to play in this story than you might think. So this movie made $500 million gross, right? That's an enormous amount of money. That's an enormous number of people that saw that movie. Yet our kind of collective, institutional, community response to the science fiction and the science fact in this movie was pathetic. It was non-existent. And after that, the memo telling us not to do anything went to the Times. They rescinded it. They said, no, that's not what we meant at all. Like somebody write us some talking points so that we know what we're talking about. I wrote them some talking points because of all my work that I had done on the thermohaline circulation. It's all coming together. And they sent these talking points to everybody in NASA. And then everybody protested. Why are you telling us what to say? This is totally outrageous. Like, okay. And at the bottom of the talking points, it says, you're not allowed to make these public. Okay. What? Secret talking points. Okay, this is nuts. And so the collective response from the scientific community was there were two static web pages, the one at Woods Hole, which is like, here's all our work that we've ever done on the thermohaline circulation. And then there was one at Lamont Doherty at Columbia, which said, oh my God, the overturning is going to collapse any minute. Okay, it wasn't quite that bad. But that was it. That was it. There was no engagement. There was no, let's reach out to the 0.01% of people that might have seen that movie and then had an actual question about the climate. Like, there was no outreach to that. And I was just, I was kind of appalled. I thought, well, why didn't we use that as a teaching moment? Why didn't we take something that's out there and tell people about what the real science is and how fascinating it is, and how some of the whole kind of stratospheric air coming down and freezing you solid in 10 seconds thing probably isn't going to ever happen, but there's interesting things to be said. But we didn't, and that kind of that bothered me, and I kept thinking, well, how could we do a better job? Because we're not doing a good job, and the institutions, perhaps are incapable of doing a good job. And meanwhile, there's so much nonsense out there that's going unrebutted and unchallenged. And so the discourse on climate, the discourse on the changes, is just being polluted by, a million people who don't have the faintest clue what they're talking about. And the people who do know what they're talking about, which includes the people in the room and the people at GIS and the people at the universities, are just not saying anything in public. How is this sensible? And it's not sensible, and it's not something that you can just sit back and let happen. And so, with a couple of other people, I said, we have to do something, we have to do something. And then it turns out that other people had also thought, we have to do something. And then we got together and we said, well, what should we do? And 2004 was also the summer of the blog. Right? Blogs are suddenly the thing. Right? Weblogs, what are these things? It seems like an odd thing, right? That it's so recent. It's 14 years ago. And this is there's no Twitter, there's no Facebook, there's no social media to speak of, right? There weren't even RSS readers. It was a totally different world. And so what we did was we got together and we built a blog, and we said we shall give climate science from climate scientists, which is not a terrible slogan. And we said we shall provide the context to breaking news stories that is missing in the mainstream media. We were very noble-minded about what we were going to do. And people liked it. Nature thought it was a great idea. Scientific American gave us some award. The week after we launched this, Michael Crichton came out with this totally appalling book, State of Fear, and I forced myself. I said, this is the kind of thing that we should be, and I forced myself to buy it on the first day that it was available, and then I read it, that weekend, and I'm putting in little post-it notes every time there's something totally egregiously appalling in it, and when I get to the end of the book, and this whole thing is like a forest of post-it notes, and I'm thinking, oh my God, that was a terrible book. And it was a terrible book. There's lots of people running around, and then stop. I'm going to give you a 4-page lecture on some totally random bullshit aspect of climate change. And everything just stops while somebody lectures the reader. And then they stop, and then they start running around again, and then stop. Here, let me tell you about how appalling the temperature measurements are that are curated by GIS. And it turns out that Michael Crichton actually knew about GIS because he'd come to visit us. He'd come to visit us, and he said, oh, show us a little bit what you do. Talk to me a little bit about climate. And during none of the interaction that we had with him, it was me, Ron Miller, Jim Hansen, did he ever actually ask a question that would imply that he didn't understand what was going on. So it was just the whole thing was just it was very odd. Anyway, so we're blogging, and I'm writing about his book, and I think I titled my commentary "A State of Confusion." Again, because I think a lot of these people are. Some of them are genuinely confused, and some of them kind of confuse themselves just to make a political point. Crichton confused himself. He was very tall. Like he was a very. So I did an event with him a couple of years later, which was a mistake. But he was a very imposing figure and a great storyteller. And let this also be a lesson to you. It doesn't matter how smart you are. You are not going to be more entertaining than somebody who's a professional entertainer. Like, you're laughing at my jokes, but I'm shit, right? I am. So, typical party conversation, kind of 2009. Right? So what do you do? I work at NASA on climate change. I was single at this point. No, you don't. My uncle says it's all a hoax anyway. I go, well, actually, oh, God. So this actually happened to one of the people at GIS now. She's in a bar downtown New York, and I think she was single at the time, and like she's standing at the bar, and some guy comes up to her, and he says, hi. And she says, hello. And he says, I work at NASA. And she says, oh, really? Which of the, like, because I know some people at Goddard and some people at Marshall, and we're working with some people at JPL, and it's like, so which bit do you work with? And he goes, okay. So I started doing other things. I wrote a book, which was a collaboration with some photographers. And it turns, so the actual idea for this came about from the photographers. They put together an exhibition of photos of related to climate change, and they said, "Oh, can you just do the captions?" Like, 'cause I knew one of the photographers from a different part of my life. And he says, "Can you do the captions?" And I said, "Sure, I'll help you with the captions." And the captions turned into a book proposal, which turned into a book, which turned into this, which is lovely. And I still have 400 copies in my cupboard in my office if anybody cares to take them off my hands. And it was very good. It was moderately successful, and it looked very good. Meanwhile, my boss was getting arrested, and totally coincidentally, I was named as the director of GIS a couple of years later. I've continued to, get better at communicating. A big step forward was doing a TED Talk where they were really very helpful in kind of forcing me to think about what it was that you were saying, how you say it, how deep you can go, and it turns out you can go deeper than most people think, because people are actually interested in this, they're curious about it, they can be taken into the details of the science far more easily than we often anticipate. And that's been moderately successful. 1 million people or so have seen it, but like compared to Zoe Suggs, I'm still in kindergarten. But then there's this weird thing that happens, right? Some of you must know who. Oh, yeah. Yes. Okay. So there's some Buffy fans here, right? Okay. So this is Willow, our LGBTQ witch, and this is Evil Willow, who comes from a parallel universe, of course. And Evil Willow is everything that Willow is except evil. And it turns out that once you go outside of our little comfort zone in the community, you too will have an evil internet doppelganger. And they will have your name, they will have your place of work, they will have your publication record. But they're terrible, terrible, terrible people. They lie all the time, they make up data, they're totally not to be trusted, they beat their children, they're just horrible, horrible people. And people refer to them a lot. And if you Google me on certain websites, you will find lots of people saying really, really terrible things about you. And you're going, that's not nice. It's not nice. And it's not true. But you have to get over that. You have to understand that you are not your internet doppelganger. You are not your evil twin. In fact, you are still a perfectly fine and mostly upstanding person. But that this is just an icon. It's a hammer that people use to make a bigger point that actually has nothing to do with you. And once you realize that most of the people shouting at you have no idea who you are or what you do or anything that you feel, it's actually a lot easier to deal with. It's kind of like people coming up to me in the playground, perhaps, and they say to me, "You dirty hippie, get your hair cut." And what would you think about that? You say, well, this is an angry, shouty person, but they're very confused. I have no hair. Right? It's the same thing. They're not shouting at you. They're shouting at an abstraction of something that they don't like. And once you understand that, your life becomes a little easier. But once you venture out into the public, you will be criticized. You will. So here's an example of when I was criticized. So in 2014, some of you might remember, this is the temperature curve that GIS curates. Goes back to about 1880. You can see ups and downs associated with volcanoes and El Niños and La Niñas, and then you can see this like big kind of global warming signal that's kind of popping up there. And you can see that in 2014, it was just a little bit warmer than 2010, which was just a little bit warmer than 2005, which was actually quite a little bit warmer than 1998. And as a service to people who are looking at this, we give a press conference every year jointly with NOAA on what all of this means. And basically, we give the same press conference every year. And it's the same press, and the press conference goes something like this. This is our record year, near record year, top 5 year, blah, blah, blah. But that doesn't really matter. What really matters is the long-term trend, because that's the thing that we understand is predictable, and that's what's going to continue to move forward. Okay, so we give the same press conference every year, and people still come to it, which is interesting. And as a help to people, we said, well, so there's uncertainty in these numbers. I mean, not a huge amount, but there is some uncertainty. And so given that there's a little bit of a gap between here and here, which is less than 2 standard deviations of that uncertainty, it's conceivable that in the real world, 2010 was actually warmer than 2014, right? It's possible. And I calculated what that was using some pretty conservative assumptions. And the probability that 2014 was really the warmest year in the real world comes out to be about 38%. Probability that 2010 was the warmest year is about 23%. So in terms of years, 2014 is your favorite, right? So the odds are that 2014 was in fact the warmest year. In fact, the odds are a little bit higher because the uncertainties are correlated from year to year, so everything kind of moves up and down together. Anyway, this is an estimate of that. And this is what we said in the press conference. NASA and NOAA, they put out press releases. 2014 was the warmest year on record, and the line about the uncertainty in here disappeared in the final version, unfortunately. But the Daily Mail thought that they had something. The Daily Mail was very excited. David Rose. If David Rose ever emails you or calls you up and wants to talk to you about anything, you put that phone right down. NASA climate scientists, me, we said 2014 was the warmest year on record, but we're only 38% sure we're right. Okay, well, that's not really good. Okay, well, never mind. The funniest thing, though, was they took a stock photograph of me that was lying around somewhere, and there it is. They put me in the paper. My mother was very proud. Not that she reads the Daily Mail, of course. And the caption was the best bit. And the caption says, Gavin Schmidt of NASA's Goddard Institute for Space Studies admits there's a margin of error. Oh my God, the secret is out. The actual work that we do is not really that. That's a tiny bit of the work that we do. The actual work that we do is stuff along these lines. It's kind of attribution. How do we understand what's going on? What are the drivers of change? And so this is an animation, data visualization that we made with Bloomberg News, and where we ask these questions, and it's a very nice thing. We say, well, all of these natural things, does that explain what's going on? No. Land use changes, does that explain what's going on? No. Ozone pollution, does that explain what's going on? No. Aerosols, does that explain what's going on? No. greenhouse gases. Does that explain what's going on? Uh-huh. And so when you put these all together, you can see for yourself that the net effects of all the human factors matches the trends that you're seeing. And when you add in the natural things, what you find is that you have an extremely good and robust understanding of what has been going on. And this is just in the surface temperature. You can add in your understanding of the ocean heat content changes, the top of the atmosphere fluxes, the stratospheric changes, all of those things, and you end up with a very, very strong and robust result that this trend that we're seeing here, it's us. And you don't need to know that very precisely. It's us. And that seems to be something that is still contested for various reasons. The interesting thing about this graphic, and I think this gives you a sense of the work that we're actually doing, is that there's about 6,000 pieces of information that went to make all of the lines that you saw. One for each year, the error bars, the different runs. Each run was like 5 different ensembles. And the amount of data that we had to crunch in order to get those 6,000 points of information was about 1 billion times larger than what you're actually seeing. When people were writing papers in the 1980s, you did not have to do quite so much data reduction in order to get one graph, because you only did one run. There was much less data to average, and But now things are different. We live in a big data world, and while we can pull like this one story out of that massive amount of data, how much more interesting stuff is in that billions of bits that we haven't yet been able to pull out. And so that's really what we spend our time actually working on. And this was huge. This was actually the most viewed data visualization on the whole of the Bloomberg media site for over a year. So this has been very useful. So coming into 2017, 2016 was, in fact, again, the warmest year on record on the tails of 2015, which was also the warmest year on record, which on the tail of 2014, which was only 38% sure it was the warmest year on record. And I get, so this is the third time in a row that my name was on the front page of the Times. Yay. And the interesting thing here is that, so it's a joint press conference with NOAA and NASA. So NASA has its data set, NOAA has its data set, and we have this little competition about whose data set makes it into the graphic. Ha, 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 ha. Suck on that, NOAA. They made it in the Washington Post, but that's not as interesting. So what do we actually do? Right now, we're gearing up for this thing here, CMIP 6. Massive amount of computation that we're doing for all these different experiments to understand various processes, to make new predictions for the future, to do new analyses for the past. We're improving our model. This is clouds, this is an LES simulation, and then this is the GIST model, which is actually now looking quite good. We're now representing the MJO and Kelvin waves much better than we used to. And we're even applying the models that we have to situations that are way outside their initial design specification. We're running these models for Mars. We're running these models for Venus 2.5 billion years ago. We're running these models for exoplanets that we have yet to discover and some that we already have discovered. And it turns out that it matters. It matters that you're using a 3-dimensional climate model to understand what's going on an exoplanet. And it gives you different results than the kind of one-dimensional calculations that people have been doing traditionally to understand whether something is in the habitable zone or not. And so, and this is all, and this is the great thing about working at NASA. When GIST started, which was over 50 years ago, they focused mainly on astrophysics. Robert Jastrow was, interested in red dwarfs and black holes and galaxy formation and all the rest of it. And we had instruments. We sent instruments to Venus. We sent instruments to Jupiter. And we had to retrieve information. So we built, not me, people before, Jim mainly, built codes to understand how to retrieve information from the backscattering from the aerosols. And that stuff made it into the models that we were using in the 1970s to kind of gear up for mission to planet Earth. And suddenly we're using the stuff that we learnt applied to space. We're using it on Earth to understand how things are changing on Earth and to understand what is driving things on Earth and to make better predictions for what's going to be happening. And now that understanding has become so sophisticated and so good, including the chemistry and the aerosols and the clouds and the different phases and all the rest of it, that we can apply those same models to simulations of Venus, of Mars, of exoplanets. And it's all kind of gone full circle. And it could only have happened at NASA. This is the thing, though, that makes it not quite as fun. These are the simulations that you do for different scenarios going into the future, to the 21st century. Business as usual here is burn it all. Find every hydrocarbon you can and burn it. Aggressive mitigation would be essentially, we've already hit peak emissions and we're reducing the amount of emissions by 5–10% every year going forward. So that isn't going to happen. I really, really, really don't want this to happen. This is kind of maybe somewhere where we will end up. But look at the scale here. This is 4 degrees Celsius. This is maxed out, this scale. This is, in terms of like the history of the Earth, if you think about how cold the Ice Age was, 20,000 years ago, the Ice Age was about 4 degrees, 5 degrees colder than the pre-industrial. Really not very much. This is a planet that is one Ice Age unit in the other direction. And if you thought that the Ice Age was a totally different planet, totally different ecosystems, totally different sea level, this planet as well will be a totally different planet. I think this is something worth avoiding. Even these serious mitigation scenarios, which is something we may end up with, look how warm it is in the Arctic. This is not consistent. This is not coherent with existing summer ice in the Arctic.
That's what we're getting now.
I'm sorry?
Looks like the anomalies we're getting now.
It's
Yes.
maxed out. It's way more than foreseen.
Yes, yeah. So it is way more than foreseen. And the changes that you're seeing here, the implication that this has for sea level, look at West Antarctica, look at Greenland. What is the implication for sea level? We don't yet know. But the last time that the planet was this warm for any length of time, sea level rose 25 meters, right, which is in the Pliocene. These are non-trivial issues, and they have non-trivial consequences. And you find yourself in the position that Sherwood Rowland found himself in after he discovered the chemistry that was leading to ozone depletion. And this is many years later. This is in 92, I think. He says, what's the use of having developed a science good enough to make predictions if, in the end, all you're willing to do is sit around and wait for them to come true? And he's right. It is not good enough to sit around and wait for these things to come true. We have an ethical responsibility to tell people about what it is that we have discovered. And that sometimes clashes with our institutional responsibilities to just get on with the job. But it's something that we have to deal with individually all the time. And it's just something that I've thought very deeply about when I have become like a public scientist and like a public scientist. I play one on TV sometimes. And in going forward, we always have our two hats. We have our scientist hat, which when we're wearing that, we take pride in the idea that we have wrestled information from the universe, encapsulated it in theory and in code and in models, and made predictions that have come true. And we go, yay, us. How smart are we? And then there's the citizen, which says, that thing that I predicted that came true, I didn't actually want that to happen. I predicted ahead of time that 2016, like a year ahead of time, that 2016 would be the warmest year on record, and I was vindicated. Yeah, it's not something we want. And so we have this dilemma. We are predicting things that we do not want to happen. And that puts us in a very odd position. But it's not one that I think that we can't deal with, but you do need to think about it. Meanwhile, I work at NASA, so I can do fun things. So we published a paper on Monday, which came about from discussions with Adam Frank, who's an astrobiologist at the University of Rochester, and what we said was, well, what's the geological impact that we're going to have right now? Right? We can calculate these things. The change in carbon isotopes, global warming signals, increased sedimentation, extinctions, faunal radiation, increased spikes of heavy metals, all sorts of things, layers of plastic. You know, we know what impact we are going to have on the geological record. But has anything like that happened in the past? And the answer is, yes, actually. There was this thing in the Paleocene, and there was this thing in the Cretaceous, and there was this other thing in the Cretaceous, and there was this thing in the Jurassic. And it turns out that there have been things that have happened a little bit like this all through Earth's history. And the question then arises, I know this is not likely, but how do we actually know what caused those things? What are the clues? Do we know? Do we really know? And so this is a paper that explores that concept a little playfully. And this is the graphic that the University of Rochester made for us with the idea of intelligent fossil fuel burning dinosaurs sometime in the Cretaceous. That's just playful. But again, I get to do that because I work at NASA. And people like this kind of thing here, I think. So, typical pie conversation now. What do you do? I just wrote a paper about the detectability of ancient civilizations millions of years ago and how that relates to astrobiology. Cool. Lizard people are real. Oh dear. Thank you very much.
I'm going to make some comments. Wonderful. You are one of the funniest people I've ever seen.
For a scientist, you love
that. I really enjoyed this. It's a 15% chance that it's one of the better talks that I've heard. We're going to put out a paper hopefully this week about global warming where we're using the AIRS data. Yeah. And in fact, 2017 was the second warmest year, in spite of a La Nina, which was probably cutting it down. We can talk about that. But you showed your predicted with moderate mitigation. There was something interesting in that picture.
Yes.
And because it's what we're seeing now. It shows a La Nina, it shows an El Nino trend. Yes. Is the ocean expected to, right now it's an oscillatory thing, but your predictions predict the ocean to actually be warming. That caught my eye. It looks just like the anomalies we have now.
Right. So different models differ on the predictions for ENSO. And there's good theoretical reasons for it to go one way, and there's equally good theoretical reasons for it to go the other way. And the models do a bit of both. And so it's one of those things where, you know, do we trust that we have enough of the physics of El Niños and Rossby waves and the like on the equator for those things to be credible? The answer is no, not really. And so there's still a big question mark there. So this is what our model does. Other models do something a little bit different.
It looked a lot like what we're seeing right now.
I mean, so the overall pattern that you see, you know, warmer on land than on the ocean, warmer in the north and in the south, warmest of all in the Arctic, some warm patches in near the Antarctic Peninsula, slight cooling in the North Atlantic, is very, very similar to the pattern that you're seeing, the trends over the last 50 years. So yes, and the models produce those things for this same period. So.
So when I update my public talk
each year. I make use of the web tools that you have for exploring the GIST data. Thank you for whoever puts those together.
If you have any comments on those or how we can improve them, we're always happy to have suggestions.
I'll save those for offline. But this talk really made me, so when I generate something from that, then I can show people that in the Arctic, where I'm working now, that we're already at a winter anomaly in the 7, 8 C range, which is astonishing.
Yes.
And the presentation made me think: do we need a bigger boat? Do we need a different scale in what we're showing to the public? Because those projections would look really different if it wasn't all saturating at 4C. And I mean, there would be some insane colors.
I chose the color bar, so it's not really an accident how that looks. But yeah, I mean, the bigger problem though is that people don't viscerally understand what 1 degree C in a global mean temperature means, right? And so one of the most effective things that I've done when I talk about these things in public is not to use temperature units at all, but to put things in the context of the last ice age and the Pliocene and things that the planet has actually seen before. Because that gives you an appropriate scale. Like the numbers, like you have to think too hard for those. Whereas the changes that we're seeing and the comparisons to previous like massive changes in the climate, they're much more visceral. So I think we can get hung up with the numbers. So I would recommend never using numbers actually. Yeah, no. So we work together on that. Yeah. Yeah, like all the way at the back.
Yeah, you talked a bit about your experience as an early career researcher, where you had this kind of pretty long time period of, can you hear me? Yeah. Kind of exploring the climate models and different components and coupling them together, and you didn't seem to be under too much pressure to, publish or perish. Any comments as to how that's aided your ability to be a good climate communicator and maybe the struggles of early career researchers now and how we can become good climate communicators?
That's 2 questions. So let me answer the last one first. To become a good communicator, what you need to do is communicate. And you will fail miserably many times, and then you will get better at it. It is not a God-given talent to be a good communicator. It is a craft. You get better at it with practice. And if you pay attention to the audiences that you talk to, and you understand where they're coming from or what they understand, and know your audience, it remains the key thing for communicating, and you can get much better, and you can talk to people who've communicated about this particular subject a lot, and you can have like a crash course in things to do, things not to do, that will be very, very useful. Now, as an early career researcher, what were the things that I would say? GIST was a very interesting place, and I hope that under my direction it remains an interesting place, because there is an overall mission, right, that is very much focused on improving these models, keeping them up to date, making them better, using them in interesting ways to compare the data and get information about the real world. But there's always been room for people to pursue things on the side. Right? It is not a very hierarchical organization, and the people there that do well understand that they have one foot in each kind of area. So there are things that you can be doing that push everybody forward, and there are things that you can do that really only you care about that may end up being key for pushing everybody forward, but you don't know that ahead of time. So Google runs on a similar approach. You've got directed work 80% of the time, and then 20% of the time is your own to do interesting things. And 99% of their interesting things go nowhere, but 1% of those interesting things that interested people did turn out to be the next big killer app that they put on the site. not quite sure that the odds are similar at GISS, but a lot of the stuff that we started off, that we ended up incorporating into the latest models came about because Drew Schindel was interested in the ozone hole and climate, and nobody else cared. I was interested in tracers because of my weird obsession with water isotopes, but really nobody else cared. Somebody else cared about ocean biology, and nobody else. But now it's all part of the whole kit, and so finding places where you can feel that there's a point in being there. There's a collective effort that's going forward, but that also has enough freedom for you to explore your own ideas and your own kind of out of context thinking. That was key for me, and it's not for everybody. People that want to be told what to do don't thrive in an environment like that, and people that only want to do their own thing don't thrive in an environment like that. But if you can balance those two things, then find somewhere like that, and then you've got both a little bit of security, but also the freedom to do the interesting stuff you want to do.
Okay, one last question.
Yeah, sorry.
Thank you. This is very informative. I'm curious to know if you consider the solar events or cosmic rays that interaction with the atmosphere. How do they affect climate change? Do you take those into consideration in your model?
Did you say solar effects?
Yeah.
Oh, yeah. So, yeah, absolutely. So we have a paper that is almost finished, which discusses how you put all of those different mechanisms together and what impact that gives you. So, thinking about UV increases that are larger than the total solar radiance changes, solar electron, solar energetic particle events, even modulation of ionization by galactic cosmic rays, which go in the same cycle. We can put all of those things in the models now, and we get a good match to the solar signal that you can see in the observed data. It's clearly there, and it's obviously larger in the stratosphere than it is at the ground. And it's a fascinating topic. It doesn't really change much of the big picture, but yes, this is something that I'm working on this week.
Okay, let's thank Gavin one more time.
Thank you very much.